Okay, so we are looking at sections 3.1 to 3.4 in our textbook, and we are looking at that stress-strain relationship. Okay, and the first page of your handout that you have has kind of a stress-strain curve, if you will, and the different portions of it. You need to understand what all of these things mean, all of these things, and that's where you may want to watch the video more than once, because if I say to you in the future, you know, we're in the elastic region, you need to know exactly what it is I'm talking about. Okay, E, remember E is the modulus of elasticity. It's Young's modulus. It's just the slope of the line. It's just the slope. So it is that yield stress over strain. So I could find it by, if I had values, just coming over like that. Okay. Brittle materials kind of behavior. So you could have a steel or concrete. You could have, for concrete, you could have the compression curve and the tensile curve. So you can see that difference in behavior. Whereas steel, okay, it kind of mirrors, or is that a reflection? Mirrors and reflections. So let's start with this first example. Okay. So the stress-strain diagram is for a steel bar. Here's the stress-strain diagram we're going to talk about in a minute. Determine approximately the modulus of elasticity, the proportional limit, the ultimate stress, the modulus of resilience, the modulus of toughness if the bar is loaded until it is stressed to 450 megapascals. Determine the amount of elastic strain recovery and the permanent set or strain in the bar when it's unloaded. So there's a lot going on in this question. The first thing I want you to note is down here we have two sets of values. The top is 0.1, 0.2, 0.3. The bottom is 0.001, 0.002, 0.003. And a lot of times you're going to have this type of information given. So if I look at this top, these top values, this is going for the whole curve. Okay, it is going all the way because this elastic region, the strains are so tiny. If I'm graphing on this scale right here, you can't even see this elastic region. Like, it has gone up, it is yielded over, and then it's gone up to this point right here. I can't see it, right? I can't see it. So in order to see the elastic and yielding portion, I might have to have another scale, and that other scale may be off by a factor of 100 or 1,000 or whatever. So it's only going to have the elastic and part of the yielding. Okay. If I were to use this scale to draw the entire curve, you can see we would need multiple pieces of paper to be able to draw the whole curve at this much smaller scale. So again, it's the same. This is just right here. So we have mostly elastic and some yielding. And then the top values, this is the whole curve. And because our strains are so small, as we're in the elastic region and beginning yielding, you can't even see them. It looks like it kind of just goes straight up and over. Okay? So there you have it. Determine approximately the modulus of elasticity. Okay? Modulus of elasticity. It is the slope of the elastic region. So if I want the slope, then I can go anywhere along here and I can figure out that slope. That slope is rise over run. Okay, so I can come up here and I can say, okay, that looks like about 325. And I can come down, and remember, when we're purple curve, purple numbers. So we can see that this right here is like 0.0015. So if I want the modulus of elasticity, it is that rise of stress over strain. I'm going to have 325 megapascals divided by 0.0015. It doesn't matter, millimeter per millimeter, meter per meter. It's still the same ratio. So my modulus of elasticity is 217 megapascals. Okay. So that's important because now if I told you my stress was at 100, you could calculate the strain. If my stress was at 150, you could calculate the strain. Okay, so that's number one. Determine the proportional limit. So the proportional limit is going to take place roughly where we also have yielding. So this right here, if we went over, that is going to be my yielding. That's where yielding occurs. And in this case, that's also that proportional limit. It's where we are no longer a proportional relationship between stress and strain. Okay, so that would be 325. Now it says the ultimate stress. So the ultimate stress is the ultimate that we can have. So that's going to be the peak of our curve. So our ultimate stress is about 500 megapascals. We could also then label, if we wanted to, fracture, the stress at fracture, and it's way over here. It's at 450. Okay, so we have that. The modulus of resilience. The modulus of resilience is energy. It's energy under specifically the elastic region. The modulus of resilience is this energy right here. Okay, so the modulus of resilience is, I just look at it as 1/2 base times height. It is 1/2 my strain times my sigma of the elastic. So my modulus of resilience is 1/2. 0.0015. Okay, I can't even copy that over. Okay, times the height of 325. Okay, and that would be the area under the curve. That is how we get to the modulus of resilience. And if I multiply that out, okay, if I multiply that out, the interesting thing here is we're going to have a unit switch. So if I have something that is megapascals, okay, and I have something that is a millimeter per millimeter, we're going to break this down. What is a Pascal? Pascal is a Newton per meter squared, okay, times a millimeter per millimeter, but it's also a meter per meter. And so I get a Newton over meter squared, over meter squared times meter per meter. Do you guys see anything that resembles a different set of units? Okay. This becomes a joule per meter cubed. A Newton meter over this is a Newton per meter cubed. Okay. So when I get this value of 0.0015 times 325, that modulus of resilience is 243,750 joules per meter cubed, which equals 244 kilojoules per meter cubed. Okay, interesting, huh? Modulus of toughness. So that would be the whole area. And if you're given squares, you know the units here. Okay, you know the units are what the units are when I'm looking at the whole curve, and I could count, okay, I have 1, 2, 3, 4, 5, and you could count up the squares, which I'm not going to expect you to do, but I want you to know that that's how you can approach that. Okay, so now we're going to move to the next part. If the bar is loaded, so we are looking at tensile, it's fixed, and I'm loading it. If the bar is loaded until it is stressed, so I have P is pulling it, and we are going to apply a load until we are stressed to 450 megapascals. Okay, determine the amount of elastic strain recovery and the permanent set or strain in the bar when it is unloaded. So what does that mean? That means as I load here, load, unload, load, unload, load, unload, back to the original length. When I move past yielding and I'm in any of this region, I'm going to have a permanent deformation. So I'm going to draw a big picture here. Okay, this will help. And we are going to come up like this, and then we're going to kind of come. So we're going to just kind of, this is our curve, okay? This is our curve. So this is A. And remember, A, that's going to be where I have my elastic, and we are stretching. Okay, my yield is at 325. And we are actually stretching it up to this value of 450 megapascals. Okay, so we are clearly in the non-elastic region. okay? And what I do know is that I know the slope of this is my modulus of elasticity, and our slope was 325 over 0.0015. We already did that to find our modulus of elasticity. When I unload, even though I'm in the plastic region, when I unload, it is going to unload at the same slope. Well, that's almost the same slope, okay? It's going to unload at the same slope, okay? So at 450, I can read on my chart over here to 450, right there, and I'm going to come straight down. And remember, we have to use these top values because we are looking at the top curve. And when I come down, I'm going to come down right about here. So if this is 0.1, this is 0.05, this is right in the middle, so 0.075. And this is my strain, okay? When I look at this, okay, here is this part of my triangle. This is called my elastic recovery, okay, because I'm following that slope. This is the elastic recovery. This is the strain that when I unload, so we've stretched it out, instead of it going back to its original length, we're going to stretch it out, we're going to unload it, it's going to go almost back to the original length. And this right here, this is our permanent set. Okay, this is going to be this strain right there. That's the strain that we will have a permanent strain in that bar now. So I've stretched it, so here's my original length. I've applied the load P, so we get this delta. I remove the load P, and now we are just slightly, okay, larger. We have a permanent strain. We have a permanent deformation. Okay, so it's pretty nice because it unloads at the same slope as our modulus of elasticity. So I'm going to erase these things so I have room to write. Okay, so I'm going to erase these so I have rooms to write. And when I look at this, okay, I know this value right here of 450, I know it's the same slope. So it would be nice to know how far over we go, okay? So if E equals stress over strain, the yield, okay, which is rise over run, okay, which is rise over run, then I know that this has to have the same amount of rise and run, okay? Same amount of rise and run. So I'm going to have 450 times 10 to the 6th pascals, okay, and we're going to divide that by 217 times 10 to the 6th pascals. So this is my stress, here's my modulus of elasticity, and there's my strain, okay. If stress equals E times strain, and I'm unloading it the same, then the strain at 450 equals, okay, when I'm coming back, E equals stress over E, okay? So this strain right here, okay, that is my elastic recovery. That is the base of my triangle, okay? That is the run. Okay, that is my run. So I know that this strain here is 0.00207. That is my run. So if I want to know the strain of permanent set, so this is the run. This is the base of that triangle. So this value of strain of permanent, this one right here, has to be then, okay, has to be then the strain at 450, 0.075 minus, okay, minus the base of my triangle, 0.00207. And when I subtract that out, I get that permanent set strain is 0.0729 millimeters per millimeter. And it looks like it's much bigger because this is nowhere drawn to scale. Okay, it's nowhere drawn to scale. Okay, so once again, I take my stress at 450, which is beyond elastic, and I find my strain at that point. Okay, I also know that the release back to its close to its original length follows the same slope. So if I know rise and run, I can calculate the base using that same modulus of elasticity. I can now take the strain at 450 minus that strain, which is the recovery. So my elastic recovery strain is 0.00207. My permanent set is the strain at 450 minus the elastic recovery, and that's that value right there. So how then would I find the permanent set or the strain? That's what this is. How could I find how much permanent length we have in our bar? How could I find that? Well, if this is strain, which is length final minus length initial over length initial, I can actually go back now and calculate the new permanent length of my bar. But it's important to understand elastic recovery, permanent set, and that's what we have going on. So the final length, if this was 100 millimeters long, would be 100.0729.